how are you?
Perfectly well.
Okay,
Thank
so
you.
many thanks, José Luis. So I would like to give you a brief presentation on how remote sensing can contribute to soil monitoring. In fact, this presentation was prepared with Anne-Richard Deforge, who is specialist in this field and in particular in digital soil monitoring. That's not my case. And yeah, so I thank her for helping me in this preparation. The presentation will be divided into three parts. In the introduction, in fact, I will point out the limitation of traditional soil monitoring methods. In the second one, I will show how remote sensing can be used to overcome some of these limitations. In a third part, I will provide an introduction to digital soil mapping, which very generally uses various remote sensing data as covariates. And I will conclude with a few key points and a link with the next two presentations. Yes, in the first sections, in fact, the introduction, but which will be a little long. I will first call the importance of soils and the risk of their rapid degradation comparatively to the very slow pedogenesis. I will discuss the need to define sustainable management practices for a wide range of stakeholders and the importance of soil monitoring. I will conclude with a discussion of the so-called traditional monitoring, which can contribute to conventional soil mapping and the limitations, of course, of such monitoring. So the importance of soils, as far as first we can recall its contribution to achieving various of the sustainable development goals defined by FAO in 2015, if I remember well, and especially Sustainable Development Goals number 2, 0 hunger, 6, clean water and sanitation, 7, affordable and clean energy, and 13, climate action, and also 15, life on land, and especially life in soils themselves. But we can also define the importance of soils with regard to their contribution to various ecosystem services, with, of course, the supply of biomass, the mitigation of climate change, buffering extreme water-related events and water compositions, the regulation of biodiversity, support of public infrastructures and their place as landscape elements. Unfortunately, soils can be rapidly degraded with reduced biodiversity, decrease in organic matter, seeding, erosion, compaction, waterlogging, or droughts, nutrient depletion, acidification, salinization, or pollution. And here you have values of the percent of European soils which are considered as degraded with regard to these various degradation indicators. And in contrast to this, the degradation which may be rapid, especially example for erosion, for water erosion, but not only, the formation of soil is very slow. As an order of magnitude, it takes more than 200 years to form only 1 centimeter of soil. And of course, unfortunately, this centimeter of soil can be quickly eliminated by erosion, soil excavation, etc. So good soil management requires some things. In fact, it combines to define sustainable practices to protect the soil and to try to restore, when it's possible, degraded soils. And of course, numerous solutions have been proposed, such as organic agriculture, soil conservation agriculture, etc. And in the first draft of the European of the draft European Directive for Soil Monitoring and Resilience. In its Annex 3, they proposed, the European Commission proposed a list of sustainable management practices to protect the soils. But one main an important thing with regard to this sustainable management is that it requires soil monitoring tailored to these objectives to be sure that our management is correct. So, of course, such practices are important for various stakeholders. Of course, political decision makers and actors interacting with them, such as scientists. So, scientists, of course, agronomists, farmers, and also lecturers, students. It's important, I think, for nearly all populations, including young populations. So, however, it's before defining monitoring method, it's important to define clear objectives. And I think that we have to answer preliminary to three questions. At first, what should be monitored? Is it soil health, soil function, soil elementary processes, etc., soil properties? Is it how can we measure these properties? For example, are we to sample at only one point soils, or to have more complex and complete sampling procedures? Can we use remote sensing data? And also, can we combine observation with calculations? And the last question is for what use in soil management? In fact, it may be the first question before the technical questions of what should be monitored and how. So, traditional soil monitoring and their limits. In fact, classically, they involve mainly physical samplings and laboratory analysis. Also, a few measurements can be made directly in the field. In fact, while accurate, these methods are often prohibitively expensive, slow, sparse, and infrequent. We just before discuss on the French monitoring program with only measurements every 16 kilometers. So it's not enough to have a good overview of the actual health of soils. So despite this, traditional soil monitoring remains the basis for many of the soil characterizations and of the most of the proposal in the framework directive on soil monitoring and resilience. So I will not detail the French RMQS since we just discussed on it. In fact, dealing with soil monitoring, we can use this traditional measurements for conventional soil mappings. And in fact, in this case, basic soil units or soil bodies are considered, and homogeneous zones are mapped. This is known as a discrete model of spatial variations. And in contrast, we may consider the soil as a continuum with continuous variations of properties. Yes. So, so conventional mapping is often associated with traditional soil monitoring methods with soil samplings, analysis, etc. Continuous or model of spatial variations may involve other values, other data, such as remote sensing data. Sorry. Yes. So main limits of discrete mapping of soil of spatial variations. At first, some assumptions may be not intuitive for people and difficult to describe explicitly, so they result most of time of the pedologies of soil scientists which are expert in their discipline. Of course, people have to do some simplifications, such as, for example, consider sharp boundaries between soil units and by using such approach, we have no idea of uncertainties on soil estimations, except on soil sampling points. So new requirements beyond these limitations, in fact, there are new needs and emerging needs that may be resumed by more data with better spatial resolutions and more frequent revisit times. And also another need is to have an idea of the associated uncertainties. This may lead to consider the continuous model of spatial variations as we have just presented before, which may take into account both direct soil characterizations and various types of covariates and especially remote sensing data. Upstream needs, it leads to other needs, but I will not present such needs in these presentations. So as a first conclusions of this introduction, so it has been well recognized that by the soil science community that the approaches and techniques used in legacy soil survey may not be suitable for providing the precise and high resolution information required by modern agricultural management and also by political decision makers who need assessment of soil health. And with, in fact, continuous advances in computing, remote and proximal sensing technologies, and also with advances in geographical information systems. In fact, soil surveying activities have transformed towards digitally based techniques that can provide soil information in more accurate and precise, that are more accurate and precise with regard to previously available methods. So in this second part, I will show how remote sensing can be used to overcome some of these limitations. I will first briefly present the great diversity of sensors and platforms that enable to access to various informations, but also to present several limitations. I will then briefly mention various means to access data and products, especially those proposed by the Copernicus Land Monitoring Service. However, numerous data are available from other sources and may be important for us as and are already used by the USO dashboard I will see later in these presentations. And I will finish this part by shortly discussing the possibility to combine remote sensing data with other data and models as already done by this USO dashboard. So the first idea is that various sensors are available, thermal sensors, passive radar, radar multispectral, hyperspectral, LIDAR, passive gamma ray spectrometry, etc. for various platforms and of course at first satellites, airborne platforms or drones, which enable to access various informations. So each object or surface characteristics can be identified for passive sensors exclusively. Yes, each object our surface characteristics can be identified by its unique spectral signature and or fingerprint at various wavelengths. And in fact, there are mainly two techniques, even we can mention others. There are mainly multispectral sensors and hyperspectral sensors, which are distinguished mainly by the number and width of the spectral bands, a limited number of large spectral bands for multispectral sensors, and a great number of much narrower, closely spaced spectral bands for hyperspectral sensors. Of course, hyperspectral sensors have greater potential in terms of their ability to detect, identify, and quantify surface compounds. But this technique is more recent and have some practical constraints. In terms of revisit times, in fact, these techniques enable to have a shorter time. For example, I don't remember exactly, but I think that Sentinel-1 and Sentinel-2 have revisit times of approximately 5 and 6 days. So with also, yes, it's sufficient. And other techniques include gamma ray spectrometry and thermal remote sensing. One important thing dealing with gamma ray spectrometry is that it's one of probably the only techniques which enable to access information not only on the surface of the soil, but also at 30 centimeter depth and sometimes at deeper depths. Dealing with active sensors, by contrast to passive sensors, they generate image by illuminating the target area, by emitting their own signal and then recording the reflection or backscatter of that signal from the Earth's surface. Of course, the best known sensors are radar, which are widely used to monitor soil moisture and soil surface roughness. But there are also various other active sensors, especially LiDAR sensors, which may enable many additional things, but probably more dealing with the vegetation over the soils. Dealing with the platforms, of course, satellites are the most used platforms. They enable large geographical coverage by passive sensors and high revisit frequency with the possibility of assessing data in real time or near real times. Dealing with the revisit frequency, as already said, it's approximately 5 to 6 days for Sentinel-1 and Sentinel-2 satellites. Dealing with their spatial resolutions, it may be a 10 square meter for these two satellites, depending on the sensors. In fact, the limitations are to the altitude and in particular the ability of multispectral and hyperspectral sensors to penetrate the clouds. And other platforms include, of course, aircrafts and drones. They can be used to achieve better spatial resolutions and to overcome the problems of cloud covers mentioned above. They are not suitable for descriptions on a global scale, of course, but they can be used either for local studies or prior to placing sensors in orbit on satellites. So most of the data are made available for free without cost through space or governmental agency services who apply most of the pre-processing steps, allowing to assess directly the surface products without atmospheric disturbance. You can thus find products supplied by national agencies, for example, the CNES in France, by, of course, the European Space Agency, by various services at national or European levels, such as, of course, Copernicus Land Monitoring Service, and other hubs such as TEIA in France, Dynamis, Sentinel-2 hub, Copernicus Access Hub, etc., enable to access also the data. In practice, it's not easy to find the data, but you have to help of specialists at least the first times. Yes, here I have listed some examples of products proposed by the European Copernicus Land Monitoring Service, and Coin Land Cover is an important product among those products. But in fact, as already said, the user dashboard also use data or products from other agencies or services such as NASA, ISRO from India. And yes, I will present you later in this presentation the dashboard and its use of the various sensors. The last important thing here is how to use data, remote sensing data. So most of remote sensing data, several remote sensing data can be used to characterize soils. But they have to come up against several problems. So the quantities measured by remote sensing are often only covariates correlated with soil properties, not directly giving access to soil properties. Most sensors are sensitive to the presence of vegetation or clouds, as already said, and most sensors only provide surface information, also as already said. So soil characterizations may be possible for bar soils between successive crops in absence of intermediate crops, or by using coupled soil and vegetation functioning models with ancillary informations. And it leads to estimate most of the soil properties by using mathematical tools and algorithms. And these models can be models describing the functionings of the land vegetation atmosphere systems, or maybe statistical soil mapping models, which are in English generally known as digital soil models. So here it's the examples of the use of user dashboard of the user dashboard used of remote sensing data for all of the degradation indicators accessible on their web site, and all sensors encircled with a red circle are in fact not non-European Union sensors, so it's important. And you can see also that remote sensing data can be helpful to predict various soil parameters, including, for example, chemical ones. For example, you can see here phosphorus informations, etc., or informations on copper, mercury, and zinc. So now, dealing with the third and final major part of this oral presentations, on digital soil mapping, it's important, in fact, to present digital soil mapping and its general feature, its potential role, the potential role of remote sensing data as covariates that may be used in digital soil mapping, and some of its strengths to obtain map of uncertainties in the same way as a map of soil properties. Sorry, yes, the main challenge is in fact to propose new methods to present the spatial variability of soil properties, and to access such uncertainties. Sorry, oh, I don't know. Yes. So I propose you first conceptual definitions of digital soil mapping. It's the creation and population of spatial soil information systems by numerical model inferring spatial and temporal variations of soil types and soil property from soil observations and knowledge and from related environmental variables. Here an examples of prediction of soil properties and other maps of uncertainties on soil properties. Another definition is a more technical one definitions. In fact, the computer-assisted production of digital maps of soil types and soil properties. It typically implies the use of mathematical and statistical models that combine information from soil observation with informations contained in correlated environmental variables and remote sensing image, of course. And I think that this came, I cannot describe, I have not the time now, but clearly illustrate these practical definitions of digital soil mapping. I will not describe in details the history of digital soil mapping. Probably the most important is the starting point with a clocked model of Jenny in 1941. An important steps was the development of geostatistics by Matron, but you may find other literature of very good quality, for example, productions of journal in the USA. And what is probably the most important for today is the development of the Scorpan model, which is in fact used in the global soil map project on which I will have some words now. It's in fact important to present this global soil map project because in fact all digital soil map products are based on its specifications now. Its main objective is to provide a digital database of soil properties worldwide at a scale of 90 meters square. So with uncertainties and of course fully downloadable. So I will not describe this slide, which give some technical properties of the required of this project. And also this project defined, of course, also standard depths of descriptions of the soil, mandatory attributes, and but which are not limitative as for the European project draft directive. It's the same. And here you can see some productions on the global soil map projects. So with very numerous publication on these projects, Geoderma is important, but not, of course, the only journals that published information on these projects. And another important thing is that numerous databases are also already available on the web. So the Scorpan model is one very important tool for this project, and it's probably the universally the best universally recognized tool to propose a map of soil properties and a map of uncertainties using direct soil characterizations and also indirect covariates such as remote sensing data. I will not enter in the details in these presentations. Dealing with the soil data, in fact, there are many various sources of data. Remote sensing can contribute significantly to both type of data, so data directly linked with soil properties, but also covariates with indirect correlations. And perhaps at a practical important point of view, in fact, the most important, the most time-consuming part when working on digital soil monitoring is only the preparation of input data.
Sorry to interrupt, Pierre.
Uh,
Just a quick reminder that you have 5 minutes left
Okay,
because we have slightly gone over time.
Okay, I will conclude. Oh no, you're right. So I will not discuss on uncertainties, but of course, all the more you have data, all the more the precision is good with such things. And to finish with digital soil monitoring, I will just present you some examples. For example, here to assess the limestone contents of soils using remote sensing data. Here it's to assess the clay content and soil organic carbon of soils. And here it's nearly the same thing to assess soil organic carbon, but you have in fact two maps, a map of values and a map of uncertainties. And to conclude these presentations, also necessary soil monitoring method, traditional soil monitoring methods based on in-situ observations or soil samplings are costly, give estimates with low spatial and temporal resolutions, and provide no information on uncertainties outside the characterized seats. Remote sensing provides access to certain soil information or makes soil properties covariates available with the spatial resolutions and revisit frequencies that can be very high. And by using both soil data and other data, including remote sensing data, digital soil mapping makes it possible to obtain precise property maps as well as uncertainty maps. Sorry. And of course, the two following presentations will give good examples and probably will complete my presentations. So many thanks. So I will stop to share. Yes.
Thank you very much, Pierre, for this informative presentation. It was very helpful in understanding the potential of remote sensing for soil monitoring. I have a question for you, Pierre. Could you give us some examples of remote